Now we're ready for problem 17. As you can see, I've already written it here. And you can see they ask us to solve this equation, which means find the value for x that makes this equation true. And maybe there's even more than one answer. Each side of this equation, we have an exponential, which means an exponential equation or expression means it's when you have the variable and the exponent. Let me just take a minute, since now we're working with these exponential equations. When you're first learning math, you end up working with exponents a lot. You have things like 4 to the third, or we say 4 cubed. And actually, we can multiply that out. 4 times 4 times 4, which I guess is 64. Of course, we also have variables. X, the exponent's 2. We already talked about. Here's something interesting. How about I take a decimal, but I raise it to the 0 power? Sort of a trick question. You don't need your calculator for this because anything raised to the 0 power is always 1. And we even an expression like this. We have a negative exponent. Of course, the exponent is still a number, but it's a negative number, and we learned what you can do to get rid of the negative exponent. Sort of flips. In this case, since it's in the top, it goes to the bottom. Here's what I want you to notice. So far, all these examples, look at all my exponents. 3, 2, 0, 3, negative 4. Matter of fact, another example is we even had what we called rational exponents, where you have your exponent's actually a fraction. But you know what? It's still a number. However, when we get to exponential functions, the thing that really changes is now we start having variables in the exponent. That is something new. Up until now, the exponent has always just been numbers, all different kinds of numbers, but still numbers. Now we're going to start having variables up in the exponent. 5 to the x minus 2. 10 to the 2x plus 1. All right. These are all examples of exponential functions. And we're going to learn to solve these. And it can be a little tricky because we're trying to solve for x, but it's almost like you can think of x, it's like x is sort of stuck up in the exponent. It's like it's like if I want to solve for x, I want to rearrange to get x equal to something. Right now, it's like x is stuck up here. Okay, so with that little primer, let's go here. So we have two exponential functions equal to each other. Now, there are really two different ways that we're going to talk about in trying to solve an equation like this. The first way is going to be a little bit easier, and that's why we always try it to see if it works. A lot of times the first method doesn't work, but if it does work, it's a lot easier. So you always try the first method. And the first method, I'm just going to call it the same base method. You recall when we have an exponent, like over here, 4 to the third, even though in math we call this whole number an exponent, really, the exponent is really this number up here, and 4 is called the base. What if I gave you an equation like this? 4 to the x equals 4 to the 5th. Okay, both sides I have exponents. But you know what? Since my base is the same, doesn't common sense say for these things to be equal, if I have the same base, obviously the exponents have to be the same right away? I know x has to be 5. Let me do one that's a little, how about 3 to the 4th equals 3 to the x plus 7. Looks a little more goofy, this x plus 7, but you know what? I have two exponents equal to each other with the same base. Right away I say, for that to be true, the exponents have to equal each other. So I know 4 equals x plus 7. I can solve for x. In this case, x is minus 3. And I've solved that equation. Now let me keep going. Let me do one more kind of example, and then you'll see how we're going to solve this. First of all, sometimes I'll do something like this. So I'll have 3 to the x plus 2 equals 9. And they're asking us to solve this. Now at first glance, you think, well, over here's an exponent, here's just a number. And how do I solve this? Well, yes, on the right-hand side is a number, but in the back of your mind you're thinking, I wonder if I can somehow still use the idea of the same base on both sides. Well, first of all, the right-hand side is not even an exponent. But then you stop and think, hey, you know what? I got a base over here of 3, and over here I've got a 9, and then you realize, oh, you remember, you know what? 9 is the same thing as 3 squared. Because now, look what I have. If I rewrite 9 as an exponent, which is 3 squared, now I have 3 to the x plus 2 equals 3 squared. Now I end up having the same base, and therefore I can set the exponents equal to each other. In this case, I just made this problem up. X is 0. So the idea is, even when only one side's an exponent, you still look at the other side, and if you can convert that into an exponent with the same base, then you can solve it easily. So now, based upon this little quick tutorial, here's this problem. Well, let me say, the first method is the same base. Actually, most of the time, this probably doesn't work, but there are some problems where it's either the same base or you can change things to get to the same base. And if you do that, that's the best way to solve it because it's usually not too hard. But the second method, which we're going to cover in a few minutes, is logs or logarithmic functions. And we're going to talk about this. For example, if I'm given this equation, 4 to the x equals 5 to the x plus 1, I first look at it, I've got exponents on both sides, and I say, hey, let me see if I have the same base. Well, I've got a base of 4, a base of 5. Then I say, well, hey, can I somehow change one side or the other and end up with the same base? No. There's no way I can ever get the same base on each side. So therefore, to solve this one, we'll see in a little bit, that's where we have to use logs. And we'll get to that. But those are the two methods to solve these kinds of equations. First method, same base, you should go ahead and see if the same base will work, and then go and do it. If it doesn't work, we have to use logs. So here, I look at this problem. At first glance, I have different bases. But then I think to myself, I wonder if I can somehow change one or both of these to get the same base. Now this is something where it just takes some experience with math, because I realize, if I take 2, like what is 2? What's 2 squared? It's 4. What's 2 cubed? 8. And if I keep going up, eventually I realize that 2 times 2 is 4, times 2 is 8, 16, 32. I think 2 to the 6th equals 64. Let me check it. 2 times 2 is 4, 8, 16, yep. And also, you know what I realize here? I've got a 128. If I multiply this by 1 more 2, I get 128. So as it turns out, I can replace 64 with 2 to the 6th and replace 128 with 2 to the 7th. So I can rewrite this. 64 is 2 to the 6th. Now I still have the exponent. I have to still write my exponent. And 128 is 2 to the 7th. I still have my exponent. Now, if you remember, if you have an exponent raised to another exponent, what do you do with these two exponents? You multiply them. So in a sense, what I need to do is here, I need to multiply 6 by negative x, and then 6 by 26. And I end up having 2 to the negative 6x plus, if I do this in my head, 120, I think it's 156. Here, 2 to the 7th to the x, 2 to the 7x. So that, I know, seems like a lot of work, but I've now gotten to my goal where I have the same base on both sides. So now I can take the exponents and set them equal to each other. And I can now solve for x. So if I add 6x to both sides, so I don't know if this reduces or not. This number looks pretty ugly. Get my calculator. Hope I didn't make a math error. 156 divided by 13 equals 12. Wow. So I've now solved that equation. So this was sort of messy, these exponents, but the idea is I was able to replace 64 and 128 with the base of 2, and I had to do a lot of math here, and eventually I was able to end up with same base on both sides, set the exponents equal to each other, and we're on our way. All right. Actually, let me stop for now because the next couple problems are all sort of similar, the next two, and I'll just make that another video. So we'll stop for now and pick up with problem 18.